Morning all. Welcome to the second morning of the final General Assembly of the CRESCENDO project. And we'll continue with some of that. I think this project's been amazing in terms of what it's produced, and we're going to hear a bit more about that today. I'll be chairing the morning session. I'm Peter Cox from Exeter. It will be like the other days in that we've got 10-minute talks with 2 minutes of question in each case. And Hazel will remind you when you get to 8 minutes, and then I'll sort of appear after about 10 minutes. We ask that you post any comments or questions in the chat, and then we'll post some of those to the speakers afterwards, depending on time. And if the speakers can keep their, well, first of all, keep to time, but also keep their answers fairly short, we'll get through a lot. So this session is largely about ocean biogeochemistry, and we're going to begin with Lester Kwiatkowski from CNRS. All yours, Lester.
How's that? Can you see the screen? Should be fine, I think.
Yeah, that's good. That's good. Got some interesting music in the background.
Yeah, I live next to a fire, quite a few fire stations. Yeah. So the initial trickle of ocean biogeochemistry papers from CMIP6 are starting to come out, and I'll present this one here, which mainly looks at the 21st century projections under the SSPs, and later on Roland's going to talk more about the kind of mean state assessment of the models. But something that's probably worth stating to begin with is that we have reason to have some kind of confidence in the future projections of the models, both in terms of their mean states and in terms of their ability to project or historical trends. They seem to be reasonable, at least as good as previous generation models. So what did we do in this work? This is sort of following on from numerous kind of multi-model studies that have taken place within CMIPs or after CMIPs over the last kind of 20 odd years. We updated projections of a number of things using the CMIP6 ensemble. So specifically here, we're looking at surface ocean warming, surface ocean acidification, subsurface deoxygenation, upper ocean nutrient declines or nutrient changes, changes in vertically integrated net primary production. So these are fairly classic things that have been studied in previous papers and often go into IPCC reports. And we've added a couple of other things in this assessment. So we also look at benefit projections of warming, acidification and deoxygenation. And there's some assessment of seasonal cycles or of temperature and carbonate chemistry and how these change in the future. So I won't have really the time to talk about these today, and I'll concentrate on the more classic stressors or impacts that we usually assess. So this is the main figure, which I guess kind of encapsulates everything that's changed between CMIP5 and CMIP6. So these are the end of 21st century changes in the variables I was talking about. You have the SSPs shown in color, and the relative or the comparative RCPs shown in black. And you can basically see that there's greater acidification, there's greater warming, there's greater deoxygenation. So all of the colored points are further along on the right, hence greater warming. They're further down on this y-axis here. So they're acidifying more in the upper ocean or the surface ocean. There's greater deoxygenation in these models as well, and there's greater nitrate declines. Something which is slightly counterintuitive, which I'll get onto later, is that there is lesser MPP declines in the CMIP6 ensemble compared to CMIP5. So lots of this paper doesn't really have the time to go into and explore all of the processes that are driving these differences. It's more an initial look at what's changed, but some of these processes we understand very well, and so we have a pretty good handle on what the drivers of these changes are. So at least for the increase in upper ocean or surface ocean warming, we know that these models have higher ECS and TCR. For the greater ocean acidification, we know that these models, the prescribed CO2 in these simulations is higher for a given radiative forcing in CMIP6 compared to CMIP5, particularly for the high-end scenarios like the SSP585. And we know that with greater warming, we're going to get greater stratification, and that's probably going to enhance our nitrate declines and also reduce our solubility of oxygen and potentially have a greater impact on the ventilation of oxygen into the upper ocean. MPP is far more uncertain what's driving these changes in the models. So this is an area of ongoing research because not only are we seeing, so the models are still declining in terms of their projections of MPP, but that decline is far less. And we've almost got a doubling of the uncertainty relative to CMIP5. So if we look at these kind of projections in a little bit more in detail, lots of these things are very similar to CMIP5. So scenario uncertainty is far greater than model uncertainty for things such as projections of warming and acidification. We have much lower confidence in our projections of MPP, where model uncertainty can be considerably larger than scenario uncertainty. And scenario model versus model uncertainty can be fairly similar if we look at things like subsurface deoxygenation. So why are we getting greater acidification? As I said before, this is largely due to the higher prescribed CO2 concentrations for a given end-of-century radiative forcing. So very well understood and highly unsurprising. Why are we getting greater surface ocean warming? So a lot of people that are far more qualified to talk about this will maybe talk about ECS and why it's increasing in CMIP6 compared to CMIP5. If we look at the patterns of these changes, they're generally very similar to CMIP5. So we still see this kind of warming hole in the North Atlantic associated with AMOC slowdown. For subsurface deoxygenation, quite similar patterns compared to the CMIP5 models. We have large areas of the low latitudes where we're not seeing, or we don't see robust changes across in the multimodal mean. But if we break down these deoxygenation or oxygen changes into their solubility and AOU components, we have a lot more confidence in the changes in solubility and the changes in AOU than we do in their combined effect on oxygen concentrations. This again, quite similar to what was seen in the CMIP5 models. For the upper ocean nitrate declines that we see in the models, they're consistent with increased stratification. And in this paper, we also look at various metrics of stratification in the upper ocean. And you can see that, well, relative to CMIP5, there is a slight enhancement in upper ocean stratification with consistent changes in mixed layer depth as well. So it looks to be that the enhanced upper ocean warming is driving enhanced upper ocean stratification and limiting the supply of nitrate into the euphotic zone. So fairly understandable thus far. The less MPP declines with this striking influence in uncertainty. So for CMIP5, all of the models declined and their uncertainty bounds were at least all within the kind of, within this range of declines. Now we have basically no confidence or very little confidence even in the sign of change in MPP in the future. So that's at least at a global scale. It seems to be driven by a few regions in particular, particularly the Indian Ocean and the North Pacific, which showed quite large declines in MPP and CMIP5, and those declines have largely disappeared in CMIP6. So it looks like something fairly fundamental has changed in the models. Basically, the evolution of phytoplankton resource limitation and or grazing pressure under climate change has altered fairly fundamentally in at least some of the models between CMIP5 and CMIP6. And as I said earlier, this is an area where there's a lot of ongoing research. We're looking into which models are driving this change. It seems to be specifically the models that have PISCUS, so the IPSL model and CNRM model are two of the main models that actually show MPP increases in the future. And we think that the parameterization of the nitrogen fixation in the models is one of the main drivers of this increase in MPP that we see in the future. And yeah, I mean, I rushed through it, but so here's the main conclusions here are that we understand fairly well how increased CO2 concentrations are driving this enhanced acidification. Similarly, we understand fairly well the link between ECS and TCR and surface ocean warming and stratification. It gets a lot more complicated when we start looking at MPP, because we have all these effects of things like grazing pressure and light limitation and nitrogen fixation, which are parameterized differently across all of the models. And we're delving into that at the moment. And as I went very quickly, well, I guess the main take-home point is that we're not really reducing projection uncertainties, and in certain cases they're increasing. So if we have learned something, it is potentially that we didn't know as much, or we thought we knew more than we did previously. So, well, thanks to all the authors and the model developers, this was a very large kind of community-led project involving a lot of people during the first confinement. It was not the easiest thing to get done, so a lot of gratitude goes to them. And if I have a touch of time, I'll just say that we're exploring here ongoing work, at least in the IPSL model, how very small changes in how you parameterize nitrogen fixation can completely change the sign of your MPP response in the future. So this is our CMIP5, CMIP6 response, and you can see these completely different, despite SSTs increasing fairly regularly or very similarly between the two models, we have a completely different response of MPP and very different global patterns. And we're starting to pull this apart using a number of different model parameterizations.
Thanks, Lester. I think we've run out of time.
I'll leave it there.
Thank you.
Yeah, thank you, Lester. We've got a few questions here in the chat. First one's from Andrew Yool. I don't know whether you can see these, Lester, but if not, I'll read them out anyway.
Yeah, read them out if you want.
Yeah, so you show NPP potentially rising against a backdrop of generally lowering nitrate. Would phosphate help resolve this seeming disparity?
So yeah, that's Andrew's spot on, and that's basically what it is. There's a nitrogen fixation is being increased by temperature, or temperature increases. At the same time, it's being limited by the amount of available phosphate, and how those two limitations on nitrogen fixation play out in the future is to some extent set by the initial phosphate mean state, and small changes we see, and small changes in the initial phosphate mean state can completely change when temperature or phosphate limitation dominate in the future. That's the kind of take home, I guess.
Great, so we'll take one more, I think. So there's one from Christoph Heinz here. How does delta NPP correlate with delta AMOC across the models?
Haven't looked at it, Christoph. So we didn't put AMOC in this paper. So,
thank you.
That was quick. So we have got time for one more from Colin. Do you think the future NPP and Piscis models is a realistic response or too hard to say? That's a loaded question. Welcome to that one, dude.
Yeah, I think it's very hard to say. So if you look at the behavior of MPP in the new Piscis models, it's to some extent it's disappeared in the latest version of NEMO. So it might have been just a blip in model development, but I think that's probably understating the significance of this. If you look at the behavior of this version of Piscis that went into both the IPSL and CNRM model, it looks very sensible in terms of how MPP responds to ENSO over the historical. So I think it's likely that our models are oversimplifying the potential future uncertainty in MPP at the moment, or at least they were in CMIP5.
Thanks ever so much, Lester. Now I welcome Sarah Berthet from CNRS Météo-France. Sarah, are you there?
Yes, I'm trying to share my screen.
No problems. Looks like it might be working. It is. All yours, Sarah.
Okay. That's okay for you? So, if you see my screen, I'm going to present a recent work that we have published in Geophysical Research Letter, and which aims to quantify the large-scale chaotic intrinsic variability of CrCO2 fluxes at interannual timescale. It's an example of what we have done with the high-resolved ocean biogeochemical simulation during the CRESCENDO project. This work has been done in collaboration with Marion Guélen, which is a leading author and which is working at LSE in Paris. Myself and Roland, we are working at CNRM in Toulouse, and Christian Été is working at the IPSL, and Thierry Penduf in Grenoble at IGE. So here is a result from Serrazin et al. 2015, showing the low frequency part of sea level anomaly for two different numerical experiments, differing only by their atmospheric forcing. On the left, the numerical experiment had a full atmospheric forcing, that is to say with all temporal frequencies, and while on the right, it was seasonal only. That is to say that the author removed the low frequency signal from the atmospheric forcing. And here the author shows the low frequency and large scale part of the oceanic response to these atmospheric forcings. And what you can see is that the climate oscillation like IOD, ENSO or PDO are directly forced, strongly forced by the low frequency atmospheric forcing, because they are not present in the seasonal only experiment. But what you can see in this seasonal only experiment is that you still have low frequency and large scale signals in eddy active regions of the ocean. So what we know from the literature is that in forced high-resolved ocean run and under seasonal atmospheric forcings, physical fields like sea surface height or ocean heat content, or even climate relevant indices like the AMOC, are significantly affected by large-scale and low-frequency chaotic intrinsic variability. You can ask, why do we care about chaotic intrinsic variability? In fact, the estimation of chaotic intrinsic variability appears useful to disentangle the anthropogenic forcing from the natural variability of the ocean, and so to predict more accurately the oceanic variability. So the motivation of this work was to determine if the chaotic intrinsic variability will also affect biogeochemical tracers. To that end, we have used a particular numerical framework needed to isolate the chaotic intrinsic variability. We run high-resolved oceanic run because at a 1/4 degree of horizontal resolution, the viscosity is lowered compared to a 2 degree or a 1 degree run, and so ocean non-linearities and mesoscale activity exist. We also need to run an ensemble of forced ocean run. As shown in this illustration, we performed the one-member spin-up during 138 years, and in 1979, we start 3 members at a 1/4 degree of horizontal resolution, all driven by the same atmospheric forcing. And because these 3 members are driven by the same atmospheric forcing, their ensemble mean will reflect the forced variability of the ocean, and their ensemble dispersion will reflect what I call the chaotic intrinsic variability. So we performed our simulation with the NEMO ocean model and the PISCES biogeochemical model. Here you can see that all members are very similar. It's the mean of the CrCO2 fluxes for the simulated period. And you can see that their root mean squared error are very close, and also their zonal mean. But you can object, of course, that 3 members appears as a very small ensemble. So you are right, but you have to note that in 2013, Hirschi et al. Has performed an estimation of the chaotic intrinsic variability of the AMOC with only 2 members. and that their estimation was more recently confirmed by Leroux et al. In 2018 based on 50 members. So why we are confident in the estimation that we will get from our 3-member ensemble. Moreover, on the left plot here, you can see the estimation we got from our small ensemble for the chaotic intrinsic variability of sea surface 8. And you can see that it is very consistent with the estimation performed by Panduf et al. In terms of amplitude. And well, you can't see the amplitude because I don't have the color bar, but you can believe me. And in terms of spatial pattern. So by this type of comparison, we performed a validation of the chaotic intrinsic variability of physical fields in our small ensemble. To build our ensemble, we apply an initial perturbation in 1979. Which is done by an initial adjustment between the model state, which is the start date, and the current forcing, which is the same in all members. In this latitude versus time diagram of the ensemble spread of CrCO2 fluxes, you can see that the spread is maximal after the perturbation of the initial condition during 3 to 4 years, and then it decreases to reach a stable distribution. So why we performed all the results I'm going to show you on the period from 1983 to 2002. So here are the results. The decomposition of the total variability of CrCO2 fluxes into its forced and intrinsic component identifies the forced variability here as the major contributor to total variability. And you can see that the geographical patterns of the forced variability is quite similar to those of the total variability, which in turn are strikingly different from those of the chaotic intrinsic variability. The two plots on the bottom show the chaotic intrinsic variability. The last plot shows the chaotic intrinsic part to total variability. And you can see on these two plots on the bottom that the chaotic intrinsic variability is very strong in eddying region, like the Southern Ocean or Western Boundary Current, Kuroshio and Gulf Stream.
2 minutes.
Thank you. When looking at the geographical pattern of sea surface temperature, for the pattern of variability, you can see that this pattern for sea surface temperature are quite similar, quite close to those of CrCO2 fluxes. And this is a new result, but it is consistent with the strong control exerted by sea surface temperature on CO2 solubility, and so on seawater CO2 partial pressure, and ultimately on the CO2 CrCO2 fluxes. Here is the ratio of the chaotic intrinsic variability to total variability and for CrCO2 fluxes, average over some regions. And what you can see is that for the global ocean, this ratio is quite small. The part of chaotic intrinsic variability reach 5.5%, but when looking at AD active region, it ranges between 16% in the Gulf Stream region to 22% in the Kuroshio region, and is also large in the Southern Ocean band. So I will skip that, sorry. And to conclude, our work has shown that interannual chaotic intrinsic variability propagates from physical to chemical tracers in areas of strong mesoscale activity, and that this chaotic intrinsic variability contributes significantly to interannual variability of CrCO2 fluxes over the Southern Ocean and Western Boundary Current, and that it may exceed 76% locally, and that outside eddy active regions, its contribution of chaotic intrinsic variability to total interannual variability is quite low, and that outside these eddy active regions, the CrCO2 fluxes are prominently driven by atmospheric forcing. So thanks, and if you want to know more, you can ask me for the paper, and here you have the reference.
Thank you very much, Sarah. We have a couple of questions already. Nadine asked, do you know why SST and CO2 fluxes, the variability of them is not so correlated in the Southern Ocean?
Sorry, can you ask me another time?
Yes, of course. Yeah. So Nadine asked, does Sarah know why SST and CO2 fluxes are not so correlated in the Southern Ocean?
You mean, well, for me, you can see my screen.
Yeah, we can see that, yeah.
For me, they are quite correlated, so I don't understand the question. If you can see on this plot, on the intrinsic variability of CrCO2 fluxes here in the Southern Ocean, and here and for the sea surface temperature. So I'm not sure to understand Nadine.
Nadine, maybe you want to come back on that through the chat. Colin asked, would you expect the CIV to increase further if you were using a 1/12 or 1/36 degree version of NEMO?
I have to read. Yes, of course, yes. The thing is that the chaotic intrinsic variability is related to the resolution because it's related to the mesoscale activity. So, of course, I'm expecting that it will rise between the two resolutions.
Right. I think we've probably got time for one more from Andrew. Andrew Yool, could the chaos observed be significant for ocean carbon storage, or is it more about consistently relating our models to observations? So in other words, how significant is the variability, I suppose, in terms of affecting the overall carbon storage?
I don't know how to answer that. I'm sorry, Andrew, I have to think about it.
Okay, thank you very much, Sarah. We should move on. Very good, thanks very much. And there's some more questions in the chat. So you can have a look at those and respond to those at your leisure. But we'll move on now. Thank you very much, Sarah. So we'll move on now to Roland Séférian, who will be from Météo-France, and will talk to us now. All yours, Roland. Are you there, Roland?
Try to switch. Okay, do you see my screen?
We do, yeah.
Okay, perfect. So good morning, everyone. In this presentation, I will present some results that emerged from the VP5, the CRESCENDO VP5 activity that aim at tracking improvement in simulating marine biogeochemistry between CMIP5 and CMIP6. Okay, let's start with some background. So the dominant paradigm in climate modeling is that you assume that the model realism will have an impact on the reliability of the future projection and the performance of the model. And what you find in the literature is that there is 3 pathways to improve model realism. So a way to connect a generation of model N to a generation of model N+1. So you find something on the increase in complexity, the increase on resolution, and a change or update in process parameterization or update in model component, and also model tuning. The fact that in CMIP6 or in CMIP5 we have a bunch of pathways that have been explored by the various modeling group, you can ask the question of how much a given pathway can influence the model performance and the projection. So we have tried to explore this for the marine biogeochemistry only, and we have looked at the diversity of the CMIP6 model and how they address those different pathways to improve model realism. So I will focus on this first part, on does the simulate marine biogeochemistry has been improved in CMIP6 with respect to CMIP5. And I will start the review with this table. So I will show 12 pairs of Earth system model. So you have in pink cell the CMIP5 predecessor, and in red cell the CMIP6 Earth system model. And here in blue, I show what has been assessed in terms of resolution for the horizontal resolution of the ocean physics, but also the vertical resolution with the numbers of vertical layers. And to look at the axis on the change in parameterization or model component, we have the bold text that tells us if there is an upgrade in the internal physics of the model. And to look at the table, the darker color means an increase in resolution. Resolution means horizontal or vertical. For the marine biogeochemistry, it is more complex. We have reviewed the model properties in terms of food web, internal physiology and stoichiometry, organic matter cycling, and representation of nutrients. So here we have the same logic. Bold text means an upgrade internal parameterization or a totally revised model component, and darker color means an increase in complexity. So I won't spend a lot of time on this table. You can find it in the literature, in the paper. So what emerged from this table is that there is noticeable change or update. There is an enhanced vertical resolution, and the group of model is converging with an horizontal resolution of 1 degree. There is a control or moderate increase in complexity. Only the key variable and processes have been added in the CMIP6 model with respect to the CMIP5 model. And there is only 2 groups that have explored the trade-off between the complexity and the increased resolution, GFDL and CAN-ESM. So we can ask what are the impact of this update on the model performance. Sorry. So this is an overview of what we have shown in the paper. We have the 12 pairs of model, CMIP5 on the right, on the left, and CMIP6 on the right. I flagged the 5 out of the 7 CRESCENDO Earth system model. So only CMCC and ECRS are missing. And we see the model bias over this period, 1995 up to 2004, for the ocean carbon fluxes, and 1998 up to 2004 for the surface chlorophyll. And we see a difference in pattern. So I will try to summarize this in some property metrics. Here, this is the summary of the change between the CMIP5 and the CMIP6 model on the scatter plot showing the CMIP5 performance on the y-axis and the CMIP6 performance on the x-axis, with the spatial correlation between the model and the observation. So a single point is a pair of CMIP5 versus CMIP6 model. So what we see with the ocean mixed layer depths is clear. Most of the CMIP6 model have been improved with respect to the CMIP5 model. This is also the case for the ocean carbon fluxes and the surface chlorophyll. So most of the model have been improved, but the improvement is modest for the oxygen, nitrogen, and silicon. And for some model, for example, for geese, there is a substantial degradation in model performance because the CMIP6 model display worse performance at simulating surface silicon concentration than the CMIP5 model. So mostly the model have been improved. This is what we see here with this skill score diagram using a z-score. So the z-score is a relative change in a weighted average root mean square error in CMIP6 with respect to CMIP5 in percentage. So where the grid cell is green, you are happy because the model data error has been reduced. Where you find reddish color, you are not happy because you are increase the model data error. So what we see here is that in average, most of the model show an improvement. This is reflected on the multi-model average here in CMIP for the column CMIP6, but there is no clear relationship between the model performance and the resolution and or the complexity. So this is a key outcome of the review/evaluation study that we have made in VP5. So I will move on to part 2. Does the Earth system interaction and feedback involving marine biogeochemistry have progressed between CMIP6 and CMIP5? So it is another table where we have addressed the Earth system interaction and coupling. We can separate in 2 parts. The first part is on the external source of nutrients. And here we have reviewed the ice melting, the geothermal source, the sediment, the river input, and the atmospheric deposition. And the other part is the gas exchange and the represented Earth system feedbacks. I will show you a schematic. In general, more comprehensive with a better treatment of nutrients and
2 minutes.
Major trace gases that have been included in CMIP6 model. So here I show a schematic where you find the key Earth system interaction with the atmosphere, the land, the geothermal vents, the sediment or the margin, and the ice sheet with the input to the ocean. And I have sketched here the numbers of models that are represented this interaction. We have 8 to 10, so 2 more models that represent the atmospheric deposition, 4 more models that represent the riverine discharge, and so on. So for example, here only 1 model, GFDL, represents the input of iron with the ice sheet melting, and only 5 models at the end of CMIP6 represent the sediment interaction with the ocean, which is not a lot. So now if we move on the Earth system feedbacks involving marine biogeochemistry, here there is the various pathway that connects marine biota or marine emission to the atmospheric physics and the climate in general, carbon cycle, biogenic aerosol cloud feedbacks, non-CO2 biogeochemical feedbacks, and the plankton light feedback. And here we have the same. So most of the model represent the carbon cycle feedbacks, but there is almost no improvement for the biogenic aerosol cloud feedbacks. Only 3 models in CMIP6 represent these feedbacks over the 12 system model assessed. No model have been improved with the representation of non-CO2 biochemical feedbacks, and only 5, so less than the half of the Earth system model assessed, represent the plankton light feedback, which is the only one biophysical feedbacks represented in the ocean, linking ocean physics and marine biogeochemistry. So the question is, are we done? So are these coupling feedbacks have evolved in CMIP6? The answer is no. And the question that we can answer is, does it matter? And here I show you the pairs, the only pairs of Earth system model that have provide at the same time a traceable atmospheric ocean general circulation model and an Earth system model in a traceable way. I'll show you the result for the abrupt 4 times CO2. And here you have the projected warming for the atmospheric general circulation model in the x-axis and the Earth system model in the y-axis. And here if you are in the bottom right panel, it means that the atmospheric general circulation model warms more than the Earth system model. And this is the general feature that emerged from this really small ensemble of models, but this is a work in progress because there is a bunch of interaction that are present in some model and not in some other. For example, CSM2 and CSM2 WACM only differs with the interactive chemistry, and this model show same feature than CNRM, CM6, CNRM, ESM2 model. So this is a work in progress. So this is the end. I would like to thank you all, and this is a collaborative paper emerging from VP5.
Thank you, Roland. There's some questions here. Andrew Yool poses a sociological question. Was there evidence that improvement in physics was at the expense of marine biogeochemistry? Interesting question.
I think it's hard to tell, to be honest. So we have a bunch of models. We have more model in CMIP6 than in CMIP5, but we don't have the tool or the framework that allow us to address properly this question, because we are lacking of traceable Earth system model and traceable atmospheric general circulation model. I think the best way to address this question is to do what you guys have done in UK. I think it's a Leicester paper that have assessed the importance of marine biogeochemistry in the same physical framework. I think the only model that can be help us to address this question is maybe CAN-ESM, because they provide two versions of the marine biogeochemical component, one with CMOC and one with CANOE. But I think it's hard to tell a robust statement from a single model.
Okay, thank you very much. And Andrew just puts in a note to say he was thinking particularly of GFDL, but I think you covered that. Chris Jones has a question. You mentioned 3 ways of improving the model, but there are also ways of improving how we use them. For example, long spin up, long sensitivity runs, or big ensembles. How should we prioritize computing resource for complexity stroke resolution improvements versus bigger runs?
Yeah, good question. So in the one of the last slide of the talk, I present the pairs of model in terms of complexity that impact the warming, but I've done the same with the high resolution. And to be honest, what we see is the impact of the spin up more than the impact of the resolution, because you see a large non-linear behavior in course of the warming, which emerged from the deep ocean drift. So to be honest, I totally agree with Chris, but it is hard to assess all this pathway, all these leads in a single paper. So this is maybe something to investigate in the forthcoming years.
Thank you very much, Roland. We'll move on now to Andrew Yool from the National Oceanography Centre. Andrew, are you there?
I'm here. Yeah.
Good, excellent.
Oops. Just show. Is my presentation visible?
Yeah, it's there now. Which export depth matters?
Yeah, it's wrong. That's obviously not the start of the presentation.
That's all right.
How do I do this?
I have no idea, dude. You're all on your own there.
Right. There we go. We're back at the start. Okay. Yeah. Sorry.
Excellent.
Shall I start?
Yeah, all yours.
Okay. Okay. Thanks, Pete. So this is kind of work I've been doing on and off. So it's a bit kind of still a bit preliminary, and I've been looking at the just patterns of mineralization inside the ocean and how this changes in the CMIP6 ensemble. So we'll just say a little bit about background about the models and about the biological pump in general, something about how primary and export production change during the 21st century, looking a bit about how this is affected by how exactly you measure the export production, and a little bit of a look forwards. So first of all, in terms of the ocean's carbon cycle, it's driven really by we think of two pumps, a solubility one, which is a kind of physical chemical one, and a biological one. And between them, they make the ocean the kind of largest storage for CO2 in the sort of Earth system, the most dynamic one. Most of what we think of as anthrop CO2 uptake is driven by the solubility pump. So that's a kind of a combination of the solubility at the surface and circulation and ventilation of the ocean. The biological pump is, as we've already heard from a number of talks already, that's just a way by which biology transfers carbon inside the ocean interior. But because that's limited by nutrients rather than anything else, rather than carbon, we don't think of it as primarily being a way for anthropogenic CO2 to get into the ocean. But because the biological pump may change into the future, I think, as we've already seen again, we make it stronger, it make it weaker, that may have a role then in how the ocean's carbon storage changes in the future. So what I've done is I've pulled together a number of CMIP6 models and CRESCENDO models. I've actually had quite a limited set because I've been using ESGF and not all the models have all the output on there just yet. I've just listed some of the variables I'm using there. And just because I want to see the biggest kick, I've used this SSP585 scenario. So these are the model configurations used. There's quite a bit of diversity in ocean, sea ice, and marine biogeochemical models. There's 4 ocean models represented. NEMO is the most common shared one. there's a mixture of sea ice models, 4 of them as well, and there's quite a bit of diversity in marine biogeochemistry models. Of the ones I looked at, only IPSL and EC Earth share the Pisces model. Otherwise, every other model was using something different. And on the whole, the models were roughly at around 1 degree resolution, although GFDL did have about a ½ degree resolution, although they nicely regridded the model down to low resolution for ESGF. In terms of what I mean by primary and export production, what I'm thinking here is the transfer of DIC, so dissolved inorganic carbon, into organic material. That's primary production. If it sinks out of the surface ocean, I've drawn 2 horizons here, one at 100 meters and one at 1,000 meters. My 100 meters is what I'm calling exports. That's stuff leaving the sort of contact with the atmosphere, and 1,000 is where we get into the ocean interior, and that's the kind of, the 1,000 is one that IPCC themselves define as a way of sequestering carbon longer term away from the atmosphere. The export 100 meters, that's a bit more kind of arbitrary, and we'll come back to that later on. And of course, as to closing the whole system, mixing and circulation of the ocean return the DIC back to the surface and close the loop. So in terms of what the models are doing, this is primary production. This is just from a recent decade. This is the current decade we're in, 2015 to 2024, and this is just sort of showing primary production for all the models I looked at here. You can sort of see there's a number of common features, but there's also a lot of divergence between the models as well. One thing which is kind of common across the models is excessive Southern Ocean production. There are issues about how good the observational data is in the Southern Ocean. There's some suggestion that there's more production there than some of the products, the observational products would suggest, but even considering that does appear to still be a bias. And there's also quite a bit of disagreement in how much productivity there is in these, what we call the oligotrophic jars. These very, very large, they're low production areas, but they're very, very large areas. And the models, again, disagree in them. And that is one of the ocean's sort of largest biomes. And it's one of the biomes which is expected to kind of grow in size as we move into the future. In terms of what happens with export, what I'm showing here is I'm showing this is the fraction of production. So this is comparing how much production is in the surface and how much of it is crossing this 100-meter threshold that I mentioned earlier. And you can sort of see there's if you thought the models were different in primary production terms, they're even more different in terms of what they say happens next. And there's strong divergence in export efficiency, but particularly between how the models deal with production, export between the poles, the equator, and the sort of subtropical regions as well. And most suggest a kind of efficiency of export increases with latitude. So the closer you are to the poles, the more export you have. But you can also see the MPI model does quite the reverse. So there's obviously diversity in how the models respond in this way. Looking at sequestration, that's sort of similarly diverse. There are some common patterns, or you can sort of see CSEM, GFTL, and MPI have this kind of high sequestration. So this is carbon getting all the way to 1,000 meters in the model. You can sort of see that's happening in the sort of equatorial Pacific, and in other regions as well, which are associated typically with low oxygen. So these models are obviously internally, these models are increasing the efficiency where there's less oxygen to basically turn the carbon back into dissolved forms. The carbon will sink through these regions, and therefore that sequestration efficiency will be greater. Other models are kind of a bit less focused on how the efficiency behaves, and you can sort of see that our own model, UKSM, on the bottom right there, is somewhat biased in terms of it's very inefficient transferring carbon into the ocean interior. And I've got a paper doing the rounds at the moment, which we sort of look at the consequences of that for things like carbon and nitrogen and oxygen inside the ocean interior, and that's a definite bias. Like overall, this is sort of summarizing the statistics. The first 2 columns are just the primary production in the present decade and the decade at the end of the century. The third, and then I've done the same for export, and then the same for export, so sequestration. And in each case, I've also included a delta column, just sort of showing the change in these properties as you go towards the end of the century. You can sort of see some of the things that were touched on, I think, by Lester already, and that is that some of the models actually show an increase in primary production, and whereas others show a decrease. Then the decreases are, as it happens, larger than the increases. But I think this is quite different from CMIP5, where almost all models were showing a uniform decrease. And as you can see, it's about half and half for primary production. But as you go into the ocean, look at export and sequestration, you can sort of see that the models are showing that are more consistent in the behaviour. With an actual fact, only CESM shows any kind of a variation. It shows greater sequestration in the future, and that may be related, as I mentioned before, to this oxygen situation. But in general, there's quite a range. You can sort of see the spread there goes, at least in sequestration, from an increase in sequestration of about 1%, all the way down to UKSM, which has a minus almost 50% decline in sequestration. But as I say, the model already is somewhat biased there. Anyway.
2 minutes.
Thank you. And this is sort of showing the sort of efficiency of transfer. This is just looking at different metrics across the suite. And you can sort of see all the models sort of show a decreasing fraction of, so there's less production being exported to by the 2090s, and you can do, and there is all the models bar one show less decreasing fraction of production being transferred into deeper into the ocean. One of the things, however, that's quite important, though, is how we define these horizons. I picked as arbitrary 100 and 1,000 meters, but you can sort of see the models mix their depth is quite important. This defines a horizon. You can't, you should maybe get past. This is just sort of showing this slew of models here. There's a general agreement, as it happens for the models. They all show very similar patterns of mixed depth. In terms of how they change, though, there's quite a bit of diversity. There's some agreement on some locations, like the North Atlantic and the Southern Ocean, but otherwise there's quite a lot of divergence. And this could be kind of important because you can sort of see here that, depending on where you factor in your where do you count your export, it might matter. If you immediately mix very, very deeply the year after, you'll ventilate back up to the surface. So mixing is how you choose this. It can be quite important to the statistics you get at the other end. And I've just done a small. I've chosen a few select variations of these to see how much of a difference they make. And these are the sort of summaries from these. So across these metrics, and I won't go into them because we haven't really got the time, but I'm happy to discuss them afterwards. So the production, the export and sequestration always declines as you move from the present to the future. But the precise statistics actually, they vary quite a lot in terms of the total magnitude of the export and also what the change is. And some of the statistics are actually distorted by things like where the production of export is actually happening. Is it happening below the mix layer? Is it happening, just at the base of it, or even deeper? In general, the selection of a deeper horizon, it reduces the size of the apparent change across the 21st century. So the deeper you go, you start with a lower flux, and the size of the change tends to be smaller as well. And finally, the results we get the results, which I've not fully analysed, they seem to be somewhat confounded by the sort of aliasing between patterns of deep mixing and the production itself. So in conclusions, the magnitude of production for all the models is consistent, but there's different spatial patterns and different biases, and these continue as you go into the deeper ocean. The models just tend to get more divergent. As I said already, there's a divergence in the fate across the 21st century, particularly production. Export, not less so. That's more of a thing that the models inside the ocean interior are behaving more similarly. And just want to say that sort of using different metrics, it can both clarify and confound things. So just finally, I intend to expand this analysis both by taking more ensemble members and a broader range of N members, and also as more data appears at the ESGF. And I'm happy to collaborate with anyone who wants to pick up with this. Thank you.
Thanks, Andrew. We've overrun a bit, but there's some questions and comments here in the chat. I don't know if you can see those. So one's is that Mommy about using the CMCC ESM model with bacteria in it, which is just really provide you with the data.
Yeah,
Colin,
I did. Yeah.
Are we able to evaluate any of the export sequestration rates, I guess, against data?
There are other observational products, both of primary production. There are some observational products of export, but they are heavily the products. They're often the sort of syntheses of observations which aren't particularly brilliant. I wouldn't trust any of them. Even production, the surface ocean, there's a lot of diversity in what they say there. So I wouldn't entirely trust it. You can, of course, as we've done with UKSM, try to work out not so much these rates, but what it does to the properties inside the ocean. So you can evaluate, for example, internal distributions of nutrients, carbon, and oxygen, just to try to get a handle on whether you think the model is doing a good job in the first place of where these processes of export and mineralization are actually happening.
Yeah. Okay, we'll take one more. There's one from Roland here. If I'm correct, the CESM group has I guess, prescribed oxygen fields because of an issue in some overconsumption process of oxygen. Do you think it will influence your results?
I'll have to look at that. I didn't know that. It's not obvious in the results I've seen. The model just looks consistent with other models, but I can certainly see that it has this. Oxygen is very important for that model. Okay,
thank you, Andrew. We'll move on then to the final talk of the session, which is from Gerd Folberth from the UK Met Office Hadley Centre. There's a slight change of direction here because Gert's going to talk about the methane cycle and heavy mitigation scenarios. Gerd, all yours.
Thank you, Peter, and hello, everyone. I'll do the usual check. Do you hear me?
Yeah, I can hear you fine, and I can see your slides.
Okay, good. Yeah, thank you, Peter. You actually took my starting phrase away, but that's fine. So we are changing gear from the ocean to the atmosphere, and I'm going to show you some work we've done at the Met Office in terms of simulating the methane cycle in the Earth system. So I'm going to show you changes we made to the Earth system model, give you a little bit an overview of its performance, and then finally close with some results, selected results from the studies that we've done with this model. So what was the motivation? This is probably where I should start. We wanted to have a fully coupled interactive methane cycle in the Earth system as much as it's possible in these days. So it's fully emissions driven. We have atmospheric composition or chemistry going on with methane. There are removal processes. There's a coupling to the land surface via the wetlands, and so on and so forth. So we started with the release version of UKESM and then made the changes as I outlined here. We had to, I should say, generally, these models tend to be driven by surface concentrations of methane because it's actually quite hard to simulate a fully coupled methane cycle, but it's a worthwhile goal to pursue. So we embarked on it, I should say. And once we had this configuration up and running technically, we did a number of simulations, as you can see here. Of course, we need a control run, but we did basically a complete transient simulation from the pre-industrial to the end of the 21st century, which means like 250 years of fully interactive methane now. So how does it look like? How does it perform? Here I'm showing a comparison between basically the concentration-driven, the surface mole fraction of methane in a concentration-driven version of UKESM in black, and the emission-driven configuration in red, which is a color scheme that I'm sticking to throughout my presentation. So whenever you see red, it's emission-driven, and whenever you see black, it's concentration-driven. So as you can see, the models start out and agree with each other quite well for a fair amount of time, well into the 20th century. But then around the 1920s, the two configurations start to diverge in terms of methane surface mole fraction. And at the end of the historic simulation in 2014, the emission-driven configuration is about 200 ppb lower in terms of mole fraction, surface mole fraction, than the concentration-driven, which is a 20% difference. But I should also mention at that point that no tuning has been going on in terms of preparation of this model. It's just really switching from one way of driving the model to the other without adjusting anything in that process. Yeah, and I mentioned here that we find a similar methane lifetime in both configurations. So this is a good sign. But one of the reasons why you actually want to go into a emission-driven rather than a concentration-driven configuration and couple as much as you can in the model is that in the concentration-driven version of the model, the seasonal cycle or the interannual cycle here actually, what I'm showing is not as good as it could be. There are ways to improve that in a concentration-driven version, of course, because we are using only constant annual mean concentrations all over the domain. So that could be improved, but still, the fully interactive model has a much better performance when it comes to simulating the season and also the interannual variability. Here we show a comparison of surface mole fraction anomalies, and we do that, of course, because we have this bias in the model. And the comparison is with actual observations from the monthly flask methane data sets from the NOAA Carbon Cycle Cooperative Global Air Sampling Network. That's a big word. And you can definitely see that the emission-driven model performs much better in terms of magnitude and variability. So the observations here are in blue, I should point out. We also included something else in the model, which we found actually is quite useful when you want to look into how where actually these biases come from in the model. And this is a diagnostic for the residual methane surface flux, which is calculated basically based on the difference between what we would expect in the concentration-driven run and what we get in the emission-driven run. And you can then convert this difference in a mole fraction into a surface flux and make assessments about, how much extra emissions or sinks would you need in terms if you wanted to completely reproduce the concentration-driven configuration with an emission concentration run. And the important point here is actually that the residual emissions that we would need to bring these two configurations in agreement with respect to surface mole fractions is rather small. I mean, it's what I'm showing here are 10-year means with the dashed thick line, and in the background you see the annual means, and the error bars indicate standard deviations in the 10-year means. So for most of the time, actually, the extra emissions that you would need to bring the two configurations into agreement is very low. Only at the end of the 20th century, there's a marked increase in the required residual flux, but it's still confined to about or less than 50 teragrams a year, which is well within the uncertainties in both the anthropogenic and the wetland emissions separately. So that actually it's doing a quite good job here. And then finally, we used, I mean, the whole idea of having such a configuration is that you want to look into pressing problems that involve methane, and one of those is like how we can mitigate emissions, methane-driven climate change. So we did a future scenario, actually a couple of them, but I'm looking only at the SSP1 2.6, which is an aggressive mitigation scenario. And what we find is that within that, applying that scenario, the methane surface concentration would return to levels last seen would return by the end of the century to levels last seen around 1910, which is a very successful reduction. So
2 minutes.
Thank you, Hazel. Both surface concentration, surface mole fractions, and the whole atmosphere burden of methane go back to levels that have last been seen at the beginning of the 20th century. But, and that's the interesting bit, we think, most parts of the methane cycle still remain heavily perturbed. So at the end of the century, the 21st century, the emission of methane from wetlands driven by climate change and land surface change are still 30% higher than they were in 1910. And so same is true for the anthropogenic emission of methane. And that also means that conversion of methane and removal of methane at the surface will be perturbed heavily. So the methane oxidation in the atmosphere is much faster than it used to be, and also there's much more deposition of methane at the surface, 34% and 11% respectively in this case. So this leads us to say that while you can look at mitigation from or while you get the idea that mitigation is very successful under when you compare it with concentrations and methane burden, other aspects of the methane cycle remain heavily perturbed, and that has consequences, for instance, for air quality when I'm looking at the chemistry. So it is important to look beyond just concentrations or the burden. And that's one reason why we actually want to have these models to be able to look into that. So that brings me to the end of my presentation. And in the interest of time, I will leave my conclusions here because they're basically stating the plain obvious, which I've already told you. And I'm happy to take any questions if there are any.
Thanks, Gert. There are some, in fact. So I'll. I don't know if you can see the chat, but there's one from.
I will have to stop sharing to see the chat.
Well, carry on as you are. So Bill Collins says there seemed to be a lag in the modelled seasonal cycle compared to the observations. Can you learn anything about model oxidation rates from this? So he is.
So yeah, my first tentative answer is probably yes. But I would have to think about it a whole lot more than I can at the moment, and it would be actually nice if Bill, we could have a discussion about that.
Okay, great. And Colin asks, how reliable are the prescribed surface methane values for the concentration runs? I.e.,
sorry, I should have said that they are based, at least for the historic portion of the distillery, they are based on observations. So these prescribed concentrations are actually more or less the observations that we have for methane over the historic period.
Yeah, and I guess his sub-question is, how good is the coverage of the global methane measurements?
Well, not good, as usually is the case with all these measurements. We have, I think, mostly for the 20th century, we have flask data, we have ice core data, where ice cores are available. We have probably the biggest problem is always the ocean. You know, there's not much coverage in terms of measurements. The measurements tend to be clustered in Europe and North America. There's very little in the Southern Hemisphere. Usual problems, really. The only redeeming feature is that methane, due to its long lifetime, is well mixed in the atmosphere. So there is not such a steep gradient between areas. But there is a certain, well, there's a very important, I think, distribution difference, which we don't get when we prescribe constant concentrations all over in the entire domain of the surface. So I would say it's the best we can do, and it's quite okay in terms of measurements for methane, mainly due to the fact that it has such a long lifetime.
Yeah. So one final one from Pierre Friedlichstein if concentrations are 20% too low, doesn't that mean emissions are 20% too low?
Possibly, but first of all, we don't know whether these emissions are coming from anthropogenic sources or whether our wetland model doesn't produce the right amount of emissions. That's one caveat. The other one is also the removal, or the biggest sink of methane is atmospheric chemistry, and there are a lot of uncertainties around that. So we need, if that transformation, that oxidation of methane is too fast, for instance, or too slow, that would also be creating biases. And we need to do more work basically now on understanding which part it is that causes the bias. My guess it's both.
Okay, thank you very much, Gert, and thank you to all the speakers in this session. My apologies for the chairing. That means we've overrun by 10 minutes, but I think they were really excellent talks, and thank you very much for that.